Hello and welcome to this webinar regarding the selection of milling strategies. The difficulties in selecting the right milling strategy can be related to difficult to machine materials, whether you have cost pressure or whether your clamping situation is unstable. But first of all, let me introduce myself. My name is Jan Schumacher. I work as a technical trainer here at a corporate center in Munich for the Hoffmann Group. My special topics are cutting tools and clamping tools. Prior to working with Hoffmann, I have been in manufacturing for 12 years as a milling expert. Now, let's see what I have with me today. Here we have 5 abbreviations, each describing a separate, dedicated milling strategy. And what I would like to do with you today is dive a little deeper into each of those and give you a small overview, so in the end we can have a comparison of what we have seen. The first candidate on our list is HSC, and HSC stands for high speed cutting. Each of those 5 milling strategies is characterized by more or less 4 important values. The first one is VC, the cutting speed, and the cutting speed for high speed cutting application is very high. Usually you operate your tools at a very high rotational speed. Then we have the feet per tooth, which is rather low. HSC strategy usually is used to machine what you see on the right, a free-form surface, some die and molds, and therefore they have to create a very good surface quality. The 2 other attributes are AP, this is the cutting depth. It is very low here at HSC strategy, as well as AE, the engagement value, which is also very low. Let me just show you 2 small videos. In the first one, we are full slotting a hardened steel, which is not typically an HSC application, but it is used here because what other option would we have? We could use a side milling cutter, but this is also very unpredictable in hardened materials. What you can see more often is finishing of die and molds. Here we see a plastic injection mold being finished, and the acoustics is more or less like a visit at the dentist's, so not very comfortable. So what do the tools need to have? Well, usually we operate with small diameters, and these need to have highly precise geometry, very tight tolerances. They need to be very accurate at the tool geometry, and you have to have the lowest possible run out coming from the tool itself as well as from the chuck. To put it in a nutshell, high-speed cutting nowadays is used for finishing with a superior surface quality, especially found on free-form surfaces as to be found in dies and molds. We recommend the use of high-speed spindles or air spindles to further increase the rotational speed and benefit even more of the parameters of the strategy. Next up, we have HPC strategy. HPC stands for high performance cutting. Let's have a look at our dial indicators. Cutting speed is increased as well as the feet per tooth. Usually we machine at a depth of about 1 times D, sometimes a little more, sometimes a little less, with a radial engagement of up to 1 times D, which means we can do full slotting using high-performance cutting strategy. Usually, the result should look like you can see it on the right side here in the illustration. Stable machine, stable clamping situation, and a lot of chips which you have cut from your workpiece. In this video here, we see such a sample operation. This is a diameter 16 cutter cutting a slot which is 20 millimeters deep. This is a heat-treated steel, so we have a very high tensile strength, and the cutter went through as if it was butter, without coolant or anything. That has to do, of course, with the cutter itself. It uses high-performance cutting material, unequal spacing, unequal pitch sometimes, state-of-the-art coating and edge preparation. And now I would like to dive in a little deeper here. Let's have a look at the cutting material at first. Well, the cutting material in most cases is solid carbide. Solid carbide is a composition of tungsten carbide which is bound together with cobalt, and it can contain other alloying elements as well, which may optimize the grain structure to even better suit the application. The requirements of HPC cutting strategy are: we have a tool with high toughness, it needs high crack resistance, high wear resistance as well, and also high temperature resistance. And all these topics have to be addressed in the composition of the carbide itself. After the carbide is created, we can have a closer look at the tool geometry. Most tools, better to say all of them, they come with unequal spacing. Unequal spacing helps a lot to suppress vibrations. Unequal spacing was first introduced with reamers, where it helped to improve surface quality. The same effect we have here. Surface quality is not bad, but we more benefit from the other effect that we can really get rid of those annoying chatters and vibrations, which in return improves our tool life. And because of not having excessive vibrations, we can even increase the cutting parameters like cutting speed or feet per tooth. Unequal spacing often comes with another geometric twist. This is an unequal pitch. I try to indicate that here. Here you can see the pitch angle of each of those cutting edges. And you can see that these lines don't end up being parallel. Well, this is not some mistake during grinding. This is also something that can help us a lot. It furthermore suppresses vibrations to increase the tool life, of course. But this feature is particularly effective at high cutting depth. For example, during side milling. You will benefit a little less in full slots, but here it can play its cards during side milling. Next up, we have coating. Coating, of course, is a wide field of technology. Here, for example, a typical HPC tool used for machining steel is usually coated with titanium aluminum nitride or aluminium chrome nitride. What we want to achieve with that is an increase in wear resistance as well as operating temperatures. We don't want chips sticking on our flutes, so anti-friction properties are important as well. And if we want to use our tools in high temperature, we need some oxidation resistance, which is usually taken care of additional layers in those coatings. So titanium aluminum nitride is usually just the wear resistance layer. We have other functional layers as well. Next up, we have edge preparation. On the top, you can see a tool in a high magnification, which has been freshly ground. Comes right out of the grinder. And you can see that the cutting edge is not very straight. It has a little shards in it. And it's not smooth at all, although you would expect it to be. So what do? You do some post-processing, like applying a water jet or additional grinding steps to your cutting edge in order to round the edge. Now, rounding the edge, well, this sounds kind of counterintuitive, but it is not really. We talk about a corner radii of 10 to 30 micrometers, which is still enough for steel machining. On the other hand, we increased the robustness of the tool, we increased the stability of the cutting edge, we prevent the cutting edge from chipping under vibration, and so that really helps us generate a lot of more tool life. To put it in a nutshell, HPC, high performance cutting, is today's standard in roughing strategies. It can be easily programmed on any CNC machine out there. You can even use them on conventional machines, just give them a go. It is very economical in almost all materials. There are some exceptions like hardened or titanium, but basically you can do anything with HPC strategy. One thing to remember, when full slotting, you generally speaking only use 1/3 or 1/2 of the cutting edge, sometimes a little bit more. But this is the area of the cutting edge that where the wear is concentrated. So this will somehow decide whether the tool is worn or not and end the tool life. Next up, we have MTC strategy. MTC stands for multitask cutting. So it's an application on multitask machines. Multitask machines, so lathes, turning centers with driven tools mainly. The process parameters are exactly the same as we have just seen in HPC machining, except one thing, and that is a fifth dial indicator showing the cutting force. And the cutting force on multitask tools is a little lower than we have them on HPC tools. But we will come back to that later. First, I'd like to show you a small video once again. Here we can see a typical MTC application. Our milling cutter driving at reasonable cutting data through this heat-treated steel. So what is it about these lower cutting forces? Well, it's got to do with the tool itself, more in detail with the cutting wedge. If we increase our rake angle gamma here on top of that scheme, we can reduce the cutting force by a significant amount. Of course, by increasing gamma, we have to decrease beta, which is the wedge angle. And this is the one downside of these tools. We achieve a lower cutting force, but we also weaken the tool, resulting in a lower tool lifetime. There's one other feature that can help us to stabilize the process, and that is the helix angle. Our MTC milling cutters use a 45-degree helix angle. And that really pulls on the workpiece, and by using those pulling forces, we can create more stability and less vibrations in our machining situation. As a summary, I'd like to give you the following hints. If you want high material removal on machines with weaker drives or less stable machines, please try one of our MTC cutters. But the downside, of course, is increased tool wear. Next on our list is HFC, which stands for high feed cutting. Yeah, let's have a look at the process parameters of high feed milling strategy once more. Cutting speed is in a moderate range. Feed per tooth is highly increased. What is highly increased, you ask? Well, compared to a standard solid carbide end mill, where we may have 0.15 or 0.2 millimeters per tooth, with high feed cutting tools, we achieve like 10 times those values. So values of 1.5 up to 2 millimeters per tooth are quite common. In addition to that, we operate at a cutting depth of about only 0.5 up to 2 millimeters. This is somewhat the range that has established. Cutting width is usually or recommended less than 1 times D. Those tools can mill a full slot. This is not very problematic, but to achieve most of the tool life, we recommend not exceeding 80% of the tool's diameter as radial in feet. Let's have a look at a nice video once more. You can see a high feed cutter, which is rather long. It is equipped with 5 cutting edges. It is a modular tool, and each of those cutting edges is driving the tool 2 millimeters per rev. So in sum, this tool drives 10 millimeters per revolution, and that's where the insane speed comes from. I just told you this is a modular tool. This is, well, the most common scene to be found out there. HFC usually is done with modular tools, but there are solid carbide tools as well, which I'd like to show you here. You could argue if you can machine the same operation faster with an HPC tool. Well, in my opinion, it depends. It depends on the workpiece material. It depends on the overhang of the tool. So here you can see the tools, and only the very left part of those tools is used, only the top part. We don't have any real cutting edges on the side, on the circumference, so only the top is to be used. Let's summarize once again. When would I recommend to choose HFC cutting? Well, if your production is unmanned or you're planning on producing unmanned, because high feed cutting tools, they really achieve the highest tool life and process stability. Power consumption of your machine tool spindle is a little lower, is a little reduced. We can operate with long overhangs without any hassle. And problem materials are also something you can address with high feed cutting tools. Particularly suitable is the HFC strategy when it comes to machining free-form surfaces, like we can see it here on the right. because your very small depth increments already bring you very close to the finished surface, so you can get rid of some pre-finishing or post-roughing operations. And it's also particularly suitable when it comes to deep contours and pockets. Downsides, not forget to mention, it is not really ideal when you have very short travel distances in your workpiece, because your machine usually cannot accelerate fast enough so that you can generate the necessary feet per tooth. And of course, your machine has to be quite dynamic and rigid. Last point on our list is TPC strategy. TPC is a Hoffmann abbreviation, stands for trochoidal performance cutting. We operate TPC milling cutters at a highly increased cutting speed, increased feet per tooth compared to HPC. Cutting depth can be greater than 3 times D, up to 5 times D, or more precisely, up to the cutting length of your cutter. And for radial infeed, we would recommend not to exceed 10% of the tool diameter. What we can achieve then is a very nice process, which I would like to show you in the following video. Here you can see the tool side milling into solid material. Side milling, not full slotting, because these tools cannot do full slot operations. And I will just show you why in a couple of seconds. A couple of words to the workpiece material. Here we have a stainless steel. This is 304 stainless, which you usually would machine with coolant to avoid excessive heat ruining the tool life. Well, it's not really necessary here. But first of all, let's have a closer look at the tool itself. Cutting edges can be up to 5 times D long, which is something you would rather not find on standard HPC milling cutters. This end mill also comes with more cutting edges. More cutting edges generate more productivity, generate more material removal rate. More cutting edges that are ground at a lower depth into the tool result in leaving a more stable core, which is more resistant to bending forces and more mechanically stable in general. And you may recognize a small detail, a small notch on the circumference of the tool, which is a chip separator. And this chip separator helps us to get rid of the long chips by splitting them into smaller segments that can be easily evacuated. Now the question is, when would we recommend to use trochoidal milling over the other strategies? Well, it depends. Generally speaking, it is the alternative, offering the best tool lifetime compared to all of the strategies seen before. But of course, it has some limitations as well. You will generate the best value if you really need those long tool overhangs, if you need to machine deep cavities with small corner radii, or if you have to machine difficult materials like hardened steels, stainless steels, or even titanium. One downside of TPC strategy is that it requires a dedicated CAM system with a special software option to program the tool path that we have just seen in the video. Not many machine controls can do this already, so most of the time you will rely on a CAM system. And you also need a dynamic, a powerful CNC machine which is really up to date and well maintained. So that's it. We have been through 5 milling strategies, and for a short recap, I would just summarize it like that. HPC strategy, well, this is the general list of milling strategies, of roughing strategies. You do not need to choose anything else. But if it comes to dedicated problems like difficult materials, you can opt out, maybe select TPC or HFC instead. If you need to machine on your turning center, choose an MTC milling cutter. If you want the maximum tool life and maximum process reliability, for example, in automated processes, TPC and HFC is the way to go. And if it's all about material removal rate in your case, TPC and HFC will help you once more. So that's it for today. Thanks for watching. We hope that we could give you some small hints for your machining operations. Feel free to contact us using the address given, our contact form, or please contact your Hoffmann Group sales representative in person. Thanks a lot.